Sorry. He was nice enough to accept giving a talk. So he will talk about conformal field theory and the bootstrap. This will be at 4. Now, of course, it's a last-minute decision, so the talk will be pretty informal. So the next talk will be by Vieri Mastropietro from Milano on Renormalization Group and Università in solid state.
Okay. So thank you for the invitation. So I will speak of application of renormalization group idea to condensed matter problem. So starting from the 90s, a lot of people working in constructive quantum field theory has applied their techniques to condensed matter. Problems in condensed matter are a sort of ideal place in which you can apply such technique, because as you will see in a moment, of course, models in condensed matter maybe are less famous, but there are many more models that you can study. I mean, if you are limited to quantum field theory, there are only very famous models, and that's it. And in a sense, the properties are very complex, and then in a sense, there are physical realization of toy models that you can imagine. So, for instance, in condensed matter appears quantum field theory models in low dimension that in a quantum field theory context are a sort of trick to start doing some computation, but in quantum matter exists really system described by these models. Also, there is a lattice. So the lattice is not simply a regularization, but is a physical object. So in particular, I will discuss today a research line which is studying a class of systems which are attracting a wide interest in recent times, which have just an emerging description in terms of quantum field theory. So not an approximate, but really an emerging description of famous quantum field theory models. Examples are quite well known. I will focus on Latiger liquids, graphene, and topological insulator. I will say something, not too much about all the things. So why they're interesting? I mean, they have important technological application. Maybe some of you have heard of these systems, and in particular, but are also an ideal arena because to understand quantum field theory properties like renormalization. So, what I mean by this, they are described by sort of lattice regularization of quantum field theory models. So, if you now you don't need to check the quantum field theory properties to go to the accelerator and to consume billions of energy, but they are very simple system, and then you have also that quantum field theory properties appear at a much lower energy scale, and has some strange properties. So it's a sort of ideal arena both from physical and mathematical point of view to be studied. So one of the properties of such system is universality, which was already mentioned in the Kopianin talk. Universality means while most physical quantities depends on all the macroscopic details, the lattice details and so on, some properties universal. So just to be concrete, let me show you this picture, which is an experiment done on graphene recently in 2008 by the group of Gaim and Nozofelov, which got the Nobel Prize for graphene. You see, so this is a quantity I will define later, which is called optical conductivity. And the optical conductivity, this is an experiment, the points, and then there is a line. And this optical conductivity is a very sharp formula. Is E is not the exponential, but is the electric charge divided by the Planck constant times pi divided by 2. So this is a very sharp formula, and you see it is very well obtained, right? And this result is quite surprising because, of course, if you think how much these solid state systems are, they depend on a lot of parameters, molecular forces, lattices, substrate, and so on. But this result is universal. So why you get this very simple and sharp formula? Okay. In particular, why there is this result is something you get also without taking into account interaction, but the interaction, it is known that is very strong in these systems. So even if there is interaction, the result is the same as for non-interacting system. So one could say, well, but how you know that there is interaction? At the end, the result is the same as for non-interacting system. But you can compute other quantities. These other quantities show a very strong dependence on conductivity. but not this one, on the interaction, but not this quantity. So this is a very clear question. So I mean, this is a very nice question both for physicists, for mathematicians, for everyone. So why all the interaction correlation disappears? Why you get a universal result? Okay, so this is an example of problems that you get. So I think in this field the role of mathematical physics is very useful because if you make computations, formal computation, really you can get you get ambiguous result. What I mean by this, of course, you can try to compute the effect of an interaction in this quantity. You get Feynman graphs, but if you consider an effective description, this Feynman graph have these ultraviolet divergences, then it depends on how you regularize. So you have no freedom. I mean, if you regularize in the wrong way, you get a wrong result, and you don't reproduce the experiments. So really, it's something you cannot just talk, but you have to do a computation, then or you get the correct result or not. So I want also to mention that there was a big discussion in the literature which was settled by theorem. I will show you in a short time. So it's not so frequent a case in which a theorem can settle a discussion in physical literature, and then by this constructing renormalization group approach, we could settle this question. In fact, if you read the book Graphene, which is a graduate student book by Kat Nelson, you get it's written that this question is settled by this theorem. There is no discussion. But before that, there was a big discussion on why you get this line, just because it was unclear how to perform a correct renormalization. So that is quite a nice story that I want to tell you. So this is another very, maybe this is a more famous phenomenon of universality, the quantization of conductance. Maybe some of you know, I mean, it was given the Nobel Prize last year for this topological insulator, that there is an extra quantization in the whole conductivity. But and then maybe you know, this is another very nice application of mathematics to physics. This quantization of conductance is due to topological reason. It's a very nice application of geometry to physics. But all this topological argument for universality also without interaction. But experiments show that universality persists also if you have interaction. So again, this is another place in which you can apply this kind of technique. Last example, one-dimensional materials. You have this Haldane relation. Haldane got also the Nobel Prize last year. In this case, you have a more subtle phenomenon of universality. Is not, you don't have a fixed point as was described by Antti before, where you have a line of fixed points, but then the relation between exponents are universal. So this is another example that you have of universal. So these are the kind of phenomena I want to describe. So as I said, perturbative analyses are not very good for universality. First, because if you neglect lattice, you get divergences. Second, because unless you control all the series, you are never sure that you get universality. Of course, you cannot claim that is universality if you make a computation to second order. Universality comes out from subtle cancellation, if it exists. Okay, and then this ambiguous result can lead to dispute in literature. So now there are two important tools which one has to need. One is the Constructive Renormalization Group. They provide bound or correlation. I mean, bounds in this, you will see, give you regularity information on the physical quantity. These regularity properties, you will see, play a crucial role to prove or not universality. And the others are word identities. I word here lattice or emerging word identities. I will explain what I mean. Maybe for people who doesn't know what word identities are relations which are present in quantum field theory between physical quantities that you need to ensure. And if you perform a correct X renormalization group, this word identity will be verified. I will see something. So we did a lot of this research line led to several results. I will focus on a small part of this result. Let me just say some literature of more recent results, and then so for people who could be interested. So there is a book. I mean, this book is updated up to 2007, but still is an introduction. So the way in which we obtained this result is a bit not very linear, because we didn't know which were the easier problem and the more difficult problem. So we started from the more difficult, and then we come back to the easier, then we come back to the more difficult. We didn't know before doing that. So we started from this problem, which was maybe more difficult than the others. So we were stuck at for something like 10 years. But then after we understood that, a lot of other problems which we believed were more complicated appear easier than the one we solved. So I've been just describing you the So this is the construction of Latin liquid. This was the first place in which we use word identities in the renormalization group approach. So most theories which are constructed in renormalization groups are or irrelevant, so super renormalizable, or asymptotically free. This kind of theories is not asymptotically free, is as a line of fixed points. So maybe in the Copiani lecture of these days you will learn what is this. Let me just say in this way, because this is recent developments, not gentle introduction, so I will assume something. So you need to implement word identities which are cancellations, but these word identities are broken by the cutoff. So you need to take into account, so these are word identities based on the gauge invariance, which is broken by the cutoff, and then you need to take into account correlation. So then there is the construction of Thierry models, and we understood what are the chiral anomalies. Then we apply these to vertex or coupled Tc models. These are classical statistical physics models. Then we apply to the Kadanoff-Haldane for transport for spin chains. Then we apply to graphene, which is the things I will describe now. Then we apply more recently to the all conductivity. So Julian is here, and also Jausen is here. Then we applied to what is called bulk edge correspondence. I will speak about this point 567. So what was applied to Università interacting dimers, there will be a course, I think, in a couple of weeks by Toninelli and Giuliani about this. Then we apply to quasi-periodic disorder and many body localization, and also there is some application to the quantum critical point. So I will try to say something about theory the first and the second, and then you will see. So this was just an introduction. So let us start from what is the problem, so the problem of graphene. So what is graphene? Graphene is, so as I said, graphene, I don't know if everyone knows what is it. It's a single layer of graphite. So it's an object, is a bidimensional material which was discovered here in United Kingdom, by the way, by Gaim and Osoferov, and it is a lattice. It is a lattice of points in a honeycomb lattice like this. Okay. So so this is the Hamiltonian. So these are creation or annihilation operators. So these are just a fermionic operator. Then it describes the hopping of a particle from one point to the other. Okay. So the A and the B are the black and the white. So the particle can hop from here to here. What describes this kind of system? They are very well known. These are, as you remember, Copiani mentioned, these statistical physics models are lattice models. So, but here the lattice is this honeycomb lattice. This lattice exists. It's something. It's just no in the honeycomb lattice.
Is it a point that's the honeycomb lattice, or would everything work on the square lattice?
Of course, if you are in the square lattice, of course everything works, but the formalism. But the result, the physics is completely different.
Okay, so the physics is different.
Completely different. Yeah. In fact, it's completely different. You will see in a second. Of course, up to a certain point, the formalism is universal, but then when you apply to, otherwise we will live in a model, in a world which is all equal, right? Yes. They change a lot. They change the Fermi surface and so on. Of course, different materials has different properties. Otherwise, will be all, sort of gray blob. I don't know. So if everything is equal, so we are all different. So it's important that it depends. Yes, it looks strange. In fact, from a quantum field theory point of view, looks strange. But here the lattice exists, and what is it? So this thing, and this is the interaction. Okay. So these are the. Okay. So now so you have to consider this trace. This is called trace of this is still in second quantization. And then you have to consider this imaginary time Schwinger function, which are a correlation function, which were introduced also by Copiani. Okay. Now you will see why. The lattice as a role. Okay, so this is the energy of this kind of system. You see, this is very complicated. if you consider a square lattice, you get a sort of paraboloid, right? So instead, if you consider this honeycomb lattice, you have this very complicated structure for the energy. In particular, you see, if you put the density around here, you see that it is a sort of cone. And then when you have a cone, you recognize that is the typical dispersion relation of a relativistic theory. Okay, so the Fermi surface in this case is are 2 points, or these 8 points are equivalent, 2 are different. Okay. So what is also important is that if you expand this 2-point function around these cones, then you get a 2-point function which is essentially linear, very similar to a relativistic quantum field theory. In fact, so this is what I mean by these systems have an emerging quantum field theory description. So if you consider this approximation, you replace just this complicated structure by cones, then you can say for in the scaling limit, let's say this Hamiltonian is essentially the Nambu-Ionel-Lagrangian Hamiltonian for fermions, for Dirac fermions in 2+1 dimension with an interaction. Okay. But so you can consider graphene as a, so the Nambu-Ionel-Lagrangian model is a quantum field theory model which lives in the continuum. Then you can say, okay, I put a lattice regularization, and then this lattice regularization, which looks an artifact, is just this graphene. You can decide that the lattice regularization is the honeycomb lattice, and then is a sort of quantum computer. You say, I want just to put a lattice. You don't do the computer. You have this graphene. Okay, so now the game is very strict because you don't have any more ultraviolet divergences. You have your constructed quantum field theory method. So now you can do renormalization and compare with experiments. And so the experiment must be you must recover the experiments, otherwise there is something strange. Okay, so now you can do exactly the renormalization program in a real system. I mean, graphene is something very simple. It's simply the graphite in the pencil, so it's nothing very deep. I mean, so if you consider the conduction properties of that are described by lattice regularization of a quantum field theory model. Okay, so now here is the renormalization. We want to study this theory with interaction and see what the interaction does. Okay.
Can you explain why you need to do renormalization? Why can't you just compute using this interaction?
Yeah, if you consider, okay, so it depends on what you mean. If you want to, if you replace this model by a continuum model, of course, you can make it's not solvable, right? So you have to make perturbative Feynman graphs, I guess.
Yeah, you can do Feynman graphs, but why do you need to renormalize and so on?
The Feynman graphs in the okay, so yes, in the ultraviolet, of course, this theory would be non-renormalizable, as you well know, as the Nambu-Ionel-Lagrangian. In the infrared, will be super normalizable, but then you don't know. Renormalization means, in this case, you have to yes. If you want to, you can call it also perturbation theory, but you have to prove this perturbation theory is convergent, and you want to compute the corrections. So you don't want to neglect these terms.
If you are on the lattice, there are no infinities.
Yes, but still you have to make the thermodynamic limit, which will be infinity. You have to send the number. When you send the volume to infinity, you have infinite many points, so you have divergences.
It's an infrared divergence.
Yes. I'm speaking about solid-state physics. So solid-state physics is an infrared problem. There is yeah, only infrared. But maybe I should stress, is infrared, also this was said by Kupiane, they are massless particles. So this you can see this as a relativistic quantum Dirac massless particle. So you have a critical theory. So you have a pure infrared problem. But it's somewhat strange because it's pure infrared but not relativistic, so you don't have any so anyway, of course, in the infrared the theory is irrelevant. You will see all the point is just to take into account these irrelevant terms. So if you want really to prove that something is okay, anyway, well, you will see. Okay, so this was the first result. We got something like 8 years ago with Alessandro Giuliani. So if u is smaller than u0, so for small u, so this result is from one side a bit boring. So you see, you get exactly the same structure as the non-interacting case.
Can you remind me what u is?
U is just the interaction. Is this u?
Okay.
It's the coupling. It could be called yes. So if u is small, everything is analytic. So what does the interaction? The interaction renormalized in a finite way, finite because the theory is super normalizable. So just the velocity and the wave function renormalization. But let me stress that this could say, well, why we are so interested in this? Yes, of course, you could say, well, these are finite correlation. This is a series which is convergent, close to the non-interacting value. But you see, this is non-universal at all. We can compute this u, this d is not 0. Then we can compute also this object. Okay, so you have finite renormalization. Okay, of course, in the relativistic theory, this does not happen. This is just an effect of the lattice, because this in relativistic theory, this velocity would be the light velocity. Here, the theory is not completely relativistic. Then the velocity is changed, and the wave function normalization is changed. Okay, but so it is also important to note, and then there is some correlation. But this is, this is a theorem. This is analytic. So renormalization in this case means that renormalization of the couplings of the V of the Z. Okay.
And was T the coefficient of the non-interacting part? What was T? There's 3T over 2.
Yes, yes. Was T? Yes,
Coefficient of
yes,
the
yes.
kinetic.
Maybe we should call it 1, but because I wanted to put the T because T it really is a physical parameter, right? So let me just also make a comment on physics. So T and U are really something which depends on the experiments. Okay, so T is the hopping and U is the coupling. So these are parameters of the material. Okay.
No, but come on. This is a model Hamiltonian. The real material is much more.
Okay, it's much more complicated. But you will see. Yes, but even this simple model is not universal. Okay, so even if you consider a more complicated model, will be even less universal. So the question is, why in this model I can get universal conductivity? Okay, you see, these quantities are not universal at all. By the way, people see this D because this is a very well-known phenomenon in experiments that the velocity is increased a lot by the interaction. They can change the interaction, changing the substrate, and they know this dependence. So all this is non-universal. Okay, so why the conductivity is universal? So this is the question I'm just discussing. Why is exactly one? So I want to recall you the experiment. Where is the experiment? To be far. Okay, here it is. So there is no T and not U. Okay, in the model there is T and U, but in the experiment and also so everything must disappear in the conductivity, but not in the other things. Okay, so this the things. So this was the first exercise. So let me say just 2 words how we prove this. So I will be very rapid because I have not so much time. So the scheme is the classical scheme of this subject. You write everything. So these are fermions. So maybe still no one, I think, has spoken about fermions up to now. So you know the particles can be bosons and fermions. Up to now, 5, 4, and so on are all bosonic theories. If you have fermionic theory, these are described by Grassmann integrations. So P in the Psi is the Grassmann-Gaussian integration. So the notation I think is similar to the one of the previous talk, but Psi are not bosons, are fermions. Okay. Then you make this decomposition of the unity, which was a picture here. Unfortunately, it was cancelled. There was a picture here by Antti like this, and so on. So you decompose the propagator in scale and in Psi, and then you integrate scale by scale, and you get several effective interaction. Okay, so you integrate one scale and you get another effective interaction, and they integrate the other scale, and so on. So you get a sequence of effective potential.
Can I ask a naive physical question?
Yes.
The electrons who are hopping there.
Yes.
Yeah. So why it is called optical conductivity?
Optical refers to the way in which it is measured, because they send some frequency, and they see it's not a conductivity measure. It's simply putting a difference of potential, but they send electromagnetic field, and then they send the frequency to this electromagnetic field to 0. Yes. In fact, okay, I go again to the picture. Very important picture. Yes. Okay, maybe it's E, but it's omega. Okay, this is a frequency. You see, they are sending some waves with some frequency, and then they send the frequency to 0, and then it goes to a limit. Okay, the static limit is recovered as a limit of these frequencies. So this is the reason why it's called optical. Otherwise, it's the static that use. Sorry. Okay, so I wanted just to say 2 words on how it is proved. So then this V is, so it is a feature of this kind of renormalization, of this rigorous renormalization, that you're going to get, at the beginning you have only quartic terms, but then at each step you get several, you have a sum of monomials of all orders, all non-local. So in the hierarchical model you get only, you don't get this phenomenon, but in the exact renormalization group, if you don't make any approximation, you get a sum of local terms. So the V are sum of truncated expectations. So you see irrelevant terms are taken into account. This you will see is very important not to neglect the relevant terms, because this cancellation, because maybe I should stress again, I want to find this universal conductivity. So if I get some result up to constant, I will not get any universal result. I need to show that all the terms, even if constant, they cancel. Okay. So this is the Wilsonian renormalization group, and so iterating. So maybe as in the previous talk was shown some trees. It's a pity that I didn't put any tree in my slides, but I can just right. So these Gallavotti-Nicolò trees are something like this. So they are obtained in this way. You make the first integration, right? So you write this. So this becomes, so this is the sum of a truncated expectation. Okay, so you represent this as is a sum, so this plus this plus this plus this and so on. Then you do another things. So now you have to do this. Sorry, this is -1. And then now instead of V you have these complicated things. So now you call this. So again you represent this again as this plus this plus this and so on. But now this bubble is this, then this became this plus this plus this and so on. Okay. So these are these Gallavotti-Nicolò trees, which are I mean, we are using that, but it's an object which appears almost everywhere. They are in other contexts are called Zimmermann forest. In other contexts, they are related to app sectors. I mean, it's a tool which appears in any kind of renormalization. So by using that, you can prove CM bounds. But it's not enough to prove convergence because the graphs are too many. So you have so by this you can make what is called the perturbative renormalization. Now you need the non-perturbative renormalization, so you need to kill this factorial. And here, to get convergence, one has to avoid graph expansion. You use the Caianello idea that fermionic expectations are determinants, and they can be bounded by Gram bounds. So we use the determinants, or in more physical terms, you use the fact the minus due to Pauli principle in the expansion. So of course you cannot use simply this idea of determinants, because unfortunately now you have truncated expectation, not a simple expectation. Then you have to extract some decay factor to perform the integral. Then now the trick is to use this famous Battle-Bridges-Feder-Busch representation for the truncated expectation, or you can use another trick of Gaveski-Kupianen, or you can read the things on the Rivasso book. I mean, this is a very famous formula that is very combining this kind of three things. You get this analyticity result. So this is famous. So anyway, Bridges is here, but you can see a representation of this formula. What means this formula? So these are the truncated. So just I try to give an idea what it means. Okay, so this, so in the notation, okay, this C tilde means monomials in the fields. Okay, so the C tilde are these fields. Okay, Then, if you consider, you have seen if you use the with the Vick rule for the Feynman graphs, then you have to contract in all the possible ways these half lines. Instead, what this formula says is you can get the same result if you consider only a tree connecting them, and the other terms are left in the determinants. Okay, so these determinants contains all the psi which are not integrated, which are not here. And then you have to sum to all the possible t, or all the possible trees. So in this way you see you have extracted a chain of propagators which you use to perform the integration over the coordinates. Then there are also some subtle point that this is not exactly like this. So this is the sum of all the possible way of connecting. Then there is also some interpolation formula. And also you have to be sure that this interpolation formula doesn't destroy the possibility of doing the ground bounds. So the G is still in the form of the scalar product. This was understood, I think, by Lesniewski in this context, but anyway. Okay, so anyway, using this, at the end, if you neglect this t, the determinant gives you a c to the n. The g, you use it for computing the integrals. The t gives you a factorial. This factorial is eliminated, but only a factorial to a power, not to two powers. And then this gives you, in this way, if the theory is super renormalizable, you can get analyticity. If it is renormalizable, otherwise you have to make more precise renormalization. Okay, this is more or less what I said. So this is a very important point, that the in this case the theory is super renormalizable. The effective coupling decreases in the infrared. So in a sense, also you have to use a lot of lattice symmetries now. This is also an important point. In principle, the only coupling are the quadratic terms. You have non-trivial finite but not trivial wave function normalization and velocity normalization, but you can have more terms. You use some symmetry. Okay, and that's it. So this I don't want to say much more on that. Just to give a flavor on how a theorem like this is found, that I would say for the study of constructive quantum theory is one of the simplest cases. So it's very nice that this physical system is described by very simple. It's just a super renormalizable theory and so on. So let me go now. I want to. Yeah.
Running coupling constant.
Running coupling constant. Okay, sorry. Okay. So this is the way in which this kind of result is found, right? So maybe I show you again. So at the end you get this kind of representation. Okay. So the 2-point function is essentially similar to the free one up to finite renormalization. So now the point is, of course. Okay, so now the point is how we get this universality. I mean, if we believe really that is there. So one has to define the currents. You see, we are really putting the lattice with some care. So the conductivity is simply connected with the the Fourier transform of the current renormalization, the current correlation. Okay. So this is this again can be computed by renormalization group. And then this is this optical conductivity. You have to send omega to first the temperature to 0 and then omega to 0. In the non-interacting case, you get this formula. Okay, P is square over 2h. So this object here gives you P over 2. You could say, well, it's already non-trivial why this VF0, which was 3 over 2t, disappears in the final formula. That is even not that obvious, because if you made a computation using the relativistic approximation, you simply change variables. But now in this case you cannot simply change variables, so you need some argument. This computation is not completely trivial. I mean, it's not simply a scaling reason why this not depends on B0. I repeat, this is important because in the experiment you get something which is universal. If VF0 appears, then you break this universality. Okay, the VF depends on T, which is the hopping parameter. Okay, so now the problem is, of course, I can expand this in series, then I get infinite many terms. So I have a convergent series. So if the experiment says that all these terms must cancel, otherwise maybe the model is wrong. Okay, so why even if you consider interaction you get the same result? So this is another theory. So this is a result we got in 2011 with also Marcello Porta, that indeed if u is inside the convergence radius, there is no plus point. This is a point, not several dots. I mean, just point, finish. There are no others. So instead, the Fermi velocity is changed. So all the quantities are serious except the conductivity. Okay, so this in fact is exactly in agreement with experiments. Instead, if you there was a debate on this. So you see the velocity.
Why limit? I thought you said it's just a constant for any omega. Why limit for omega going to 0?
No. Why I said I never said that. It tends.
Well, your plot was pretty flat for any omega.
That is an experimental plot. This is just my limit. The plot is the experimental group. The plot in the first slide, I mean.
Yeah.
That is the plot of experiments. Looks, this is a good point. From the plot seems even more than this. That is a good, yes. In fact, this is a very interesting point. This is a challenge for everyone. I mean, is why, and we prove this in the limit with this exchange of limits. Apparently, the plot seems that not only the limits is universal, but even for finite omega is universal. Okay. That's in fact this phenomenon is still not completely understood. Because the problem is exactly this. In fact, there is still a big debate in graphene community that if you more for long range, of course, because if you make formal computation, then even and especially for finite omega, you get a lot of graphs. It is unclear if they can reproduce the plots or not. It really depends on how you perform the normalization. So this is not just an academic problem. It depends really on how you make
the comparison. This was two electron volts. This.
I mean, this is I mean, I'm sending to 0. Yes.
To 0.
Yes.
Maybe this 2 electron volts is actually 0 somehow.
Yes, but of course it would be much better here if we can really compute the second order.
It is comparable with.
No. I think it's a big cancellation which happens also at finite omega that we're unable to prove. Yes. This is really a challenge. To eliminate this limit is a challenge. I mean,
it will not be strictly universal.
Yes. In fact, maybe I should. I don't know. I'm not much time, but if you, so of course, now we get these points. Of course, if you compute the correlation, we didn't try to compute the correlation by our expansion, which unfortunately our expansion is good for bounds, but difficult to make concrete computation. But several groups using approximation, they get something. It go to 0 like this. So it seems that you must get that. Okay, but a lot of groups find different things. By the way, what is very bad, they don't get this, they get this. So before our result, almost everyone were arriving here, even at 0. But what happens? So at least we have proved that the limit is 0. So, but if it does like this or like this, we don't know. Okay.
But there must be some reason for that. I mean, the way you presented it.
Sure. No. The reason for this is very physical.
Yeah,
the reason for the other cancellation, I don't know. That's very interesting. The reason for this is easy, very, very easy. Just in 3 minutes you will see. But the reason why instead of the plots, so I mean there are two mysterious things. Why is the limit universal and why is flat? We understood why is universal, we don't know why it's flat. Okay? We understood why it's universal, but only with the short range interaction in our circle and so on. Then there is a lot of problem. What happens with real Coulomb interaction? By the way, in real graphene, U is 3. So for us, it's something like 10 to minus 10. So there is a lot of things to understand. But at least you see, we see this phenomenon. I mean, the velocity is not universal and the conductivity is universal. At least this. So maybe so I agree that this is a bit too sharp. I mean, set the question of why the limit is universal. Okay. Anyway, still open the long range case. So let's see. So you will see the proof. You will see now the proof. You will see the bounds are useful to prove this. You will see in a second. So bounds are useful to get this result almost without computation. So first of all, this is the 3-point function. So this is the current. So now there is a word identity. The word identity is simply the conservation of the electric current. So this means simply, if you make a derivative of J, then you get the mu J mu equal to 0. So you get also on the lattice you have, as we have carefully defined the current in the lattice, we have exactly defined the current. You see, why you could say why we have this strange definition, right? Is with a lot of J and so on. This is defined. This is exactly the current on the lattice. So you see, the 3-point function is related to the difference of the 2-point function. So this is an exact relation. It's not of the effective quantum field theory model. It's just of the lattice theory. Okay, and there are similar world identities for the current and correlations. Okay.
This is where the lattice matters. This is a
The lattice matters in several points. If you don't put the lattice, of course, we get. So now you can say if you don't put the lattice, then you get ultraviolet divergences because you have the Nambu-York-Lazini model, which is not normalizable. Then you put the lattice, but the lattice breaks gauge invariance. So you will not have any more this. If you put just a momentum cutoff, then you have to you choose the real lattice, which is a physical one, and then now the world identities are really relation with finite quantities. Okay.
No, but does the symmetries of the triangular lattice
Yes,
matter?
yes, this delta, yes, this delta are, of course, this delta are exactly the
No, but you would have a similar one for the.
yes, but with other delta, yes. This is special for that case. You have always a word is simply conservation of the current. This form depends on the lattice. Word is simply the conservation of current. You consider the density, you make derivative of the density, you get the commutator, then the commutator you write as the gradient times something, and this something is the current. With the
Differentiate with respect to what?
to time. The T rho, yes, is the
related to time.
yes, yes. The T rho is equal to the Okay. So finally bounds. So finally, at the moment I've not used bounds. Now I use finally bounds. So these bounds say this gamma mu nu is the current is this current correlation. Okay. So for long distances, go as 1 over x to the 4. Why x to the 4? Very easy, because we are in 3 dimension. Okay, maybe I can. If you think a moment, you understand why you get the 4. The propagator is 1 over. Okay, anyway, it's easy to see. It's 1 over x squared, and then you have 2 propagators when you compute it. So this is just essentially dimensional propagators, a dimensional bound. Okay, so this is the result of the expansion of the renormalization group. Okay, so this kind of bounds is obtained by using this renormalization group approach. Okay, so for u smaller than u0, we get this. So the Fourier transform is continuous then, because the Fourier transform is in 3 dimensions. So by using word identities, then you can rewrite this conductivity in this way. Okay. So this is already here. There is something non-trivial. There is the constant which appear in the definition is simply the value of k in 0, which is well defined because it's continuous. So k is even. So what's that? Well, then it's 0 because it's the derivative of an even function.
What was beta? Is that
What is?
Oh, that's the temperature.
That's the temperature. Yes, yes. Oh, okay. Another problem. All this is done. Finite omega, finite beta. For this approach, it's very difficult to consider finite omega and finite temperature. Very, very difficult, because we could now. I think I will say only a very, very small fraction of my talk, but I have still. But okay. But so because I did not mention that. This limit is done in the Euclidean, so one has to prove that analytic continuation can be done, which at 0 temperature can be proven. Okay, but let's see this subtle point. This subtle point is this: that this is the derivative is even. Then you would say, well, the derivative you have to make the limit to 0, so it's 0. No, because the derivative is continuous but not differentiable. Okay, so the reason why there is a finite conductivity is that. Continuous but not differentiable. Okay, so that it depends on the dimension. For instance, in 1 dimension, instead the analog of this is non-continuous, and then the conductivity is infinite. Okay, so one could say, so if it would be 0, it would be continuous. So instead of 4, you have 4 plus epsilon, you get 0 instead. Okay, but it's not. And already, on the other hand, you know that this is non-zero because we have computed the free case. Okay, but then
I'm confused though. It looks pretty differentiable if you're taking omega to 0.
this is 1 over omega.
Yeah.
Yes,
I mean,
but it's
that's
4,
the
three-dimensional.
derivative. That-
It's three-dimensional. It's d3x.
You're not talking about the derivative with respect to omega. Then.
Yes. Yes.
But if the limit exists, then it's differentiable. I mean, that's what you would mean by the derivative
Yes,
at 0.
maybe wrong somewhere.
It's the right derivative at 0.
It's the right derivative of 0, yeah. Are you saying the right derivative of the
It's
left
different
derivative?
from the left.
Oh, okay.
Yeah, sorry. Here it's wrong. Sorry. 4. Sorry. Yes. So it's this d3x over 4.
Yeah, no,
So if you make another derivative, you get x.
No, I was asking a much more simple.
No, but this is also very simple. Sorry. So d3x over x4. If you make a derivative, you have x. That's not very deep mathematics. Okay. So without this, it's okay. So, but this I want to stress because this is a sound of something, right? So if the derivative would be continuous, it's 0. We want to prove that the correction are 0. Okay. So now next now is the final mystery is solved. So if you make all this renormalization group, at the end you get this formula. This formula says that the 2-point function is equal to the free one with finite renormalization plus a terms which depends on the relevant terms. The relevant terms are these lattice effects and so on, or the relevant terms are even interaction, are even contribution from the coupling, but I mean also Z depends on the coupling, right? So anyway, you can. I have no time now to explain, but it's very natural. Everyone knows renormalization group. Maybe understand how this formula is found. You get that the current correlation is a part. The theory is super renormalizable. So as a part which is identical to the free part up to finite renormalization plus a term which depends on the relevant terms. And this term, which is the difference of the two, they are both order 1, but they are decay faster because it depends only on the relevant terms. Okay, so all these objects are universal, and so on. So this is the final formula. So at the end it's almost finished now because now once you have a formula like this, and then now you have to use the word identity. The lattice word identity says you that these Z are non-universal, but they verify this exact relation just by the lattice word identity I said. So simply this relation are found writing the analog of this formula for the 2 points and the 3 points and inserting in the word identity. That's give you an exact relation between the Z. Okay, so you get these exact relations. So all the Z disappears. So all the source of non-renormalization change, and now these are. So K is even, and also R is even. Okay, so this piece 0. So this is a number of Feynman graphs, but when you make the derivative and send omega to 0, is exactly 0 because now it's differentiable just by this theta. Okay. The theta is due to the fact that this is the contribution of the relevant terms. So the relevant terms, in other words, are not, yes, are smaller, but in which sense? They have a finite contribution, but the finite contribution is simply a bit faster decaying. Okay, so that's it. So you do that, the first term, and then the first term it remains VF, but this VF, this is exactly the non-interacting conductivity with a different VF. Okay, but then the non-interacting conductivity was independent from VF, and so it's universal. Okay, so the two steps are the non-perturbative bounds for the decay and the word identity. Okay, so of course, for coming to the question of Slava is not easy because you have really not simply to say this is even and then it's 0, but you have really to compute this R omega minus R0 and then make the analytic continuation. That's is, then you have all these cutoffs and so on. So this is a very abstract argument that says what we get. Okay, so this was maybe the simplest result, but also the most one of the better, I would say, because So maybe, okay, I have not so much time, so maybe I can give a flavor of some other things. So then we apply, it was very natural to apply this kind of things to the whole effect. There is a model which, if you add to this graphene other pieces, they produces gaps, and in these gaps, it happens that if you fix the chemical potential in these gaps, then you have what is called the quantum Hall effect phenomenon. Essentially, you can compute now the transverse conductivity, not simply the longitudinal conductivity, and then it is integer again in the non-interacting case. And then there is a phase diagram as a function of the parameters. This model is called the model, in which this sigma 1, 2 is again quantized. So in the previous case, we were considering the case without gaps. Now we have the case with gaps, and then we have this other quantization. So the whole conductivity is a subject which is very much studied. The reason why you get this integer here is related to topological invariance of the bands of these systems. So the question we addressed was why if this quantization remains like this even if there is interaction, because if there is interaction you cannot use these topological arguments, because these topological arguments are based on the single particle Schrödinger equation. Okay, so now I will have not much time, 10 minutes, but I will just then state the result, which is with Jocelyn. So again, there are apparently a lot of renormalization everywhere, but they disappear. So the result is this. Maybe show a picture. So what happens is that, what is this? You must remember the picture before. Inside, in the non-interacting case, inside was quantized and outside was 0. The effect of the interaction is that the lines are non-universal, but the value of the conductivity inside and outside is the same. Okay. So the lines, which the phase separation lines, is also a typical phenomenon which appears in the theory of universality. For instance, is related to the Kantian term which was discussed by Antti yesterday and maybe next hour. So the critical temperature change, but the value of the critical exponents remain the same. Here is a phenomenon like that. The lines are changed, which are non-universal, but the value, which is quantized, is a pure number, remains the same. Okay, so this is I wanted just to mention this. So all these kind of models are, in a sense, the simplest examples, because our theory which are or super renormalizable or even massive. So according to the renormalization group, this kind of problem is very easy, even if the result I think is interesting because you have to. So a more interesting case are the case in which there is lines of fixed points. So I thought I have very small time to say something on that. Maybe let's see if I can say something. Not easy. So now there is. So we are speaking about this bidimensional object, right? So this graphene is bidimensional. So it happens that these bidimensional objects are as we said, are insulating, where there are gaps. But you can study the surface of these systems, and the surface of these systems are essentially one-dimensional objects. And then a famous Hamiltonian, which is described in this context, is the Kane-Meyle-Hubbard model. There is a property. Now I'm very quick, but if people is interested, we can discuss. I wanted just to say some words about this kind of, just to understand. As was recent experiments, I wanted to show you maybe the most advanced results, but there is a course about that in a couple of weeks. Anyway. Okay, now you have to know this, that if you consider not periodic but cylindric boundary condition, there are edge states, so there are states which are localized at the boundary, and there is a famous property which is called bulk edge correspondence, which says that the conductance at the surface is the same that the whole conductivity. So again, what happens if we put interactions? Okay, so again we could prove, okay, maybe I switch, I just go to the result because I have just 5 minutes. Okay, let's say simply the result. So the result is obtained, this one is obtained with Marcello Porta, it was a recent result. Again, you see, now it's a very subtle phenomenon. I've not defined precisely all these objects, but this is the conductivity, what is called the spin conductivity, and these are other thermodynamical coefficients. So you see, only this object was conjectured to be universal and the other not, and indeed it is like this. So this sigma does not depend, kappa depends on the interaction. So only this sigma s does not depend on the interaction. All the other quantities depends on the interaction. By the way, there is even again, also this eta was mentioned by Antti, and maybe we'll speak again. This is the 2-point, the wave function renormalization. So you have a non-trivial wave function renormalization. You have all this non-trivial renormalization for all the quantities, except that for the spin conductivity, which is exactly universal. So this is a nice case in which you have two kinds of universality. So let me just say a couple of words just without too many details. So you see there are two kinds of universality. The strict universality in which some quantities does not depend on the interaction is 1 over pi. Omega is plus or minus 1. Okay, so 1 over pi is very universal. It does not depend on the interaction. Then there is this other kind of interaction, of universality, that says that even if all these quantities depend on interaction, they depend in this very simple form. And in particular, if you make the ratio of this, you get simple scaling relations which are conjectured by Haldane and Kadanoff before. So just to finish, I want just to say how is proved the result like this. So now you need this. I want just to mention this because and then there is a course about that, so you will learn about this. But anyway, so now we have seen now that up to now that you have bounds and word identities. Okay, word identities for the lattice. Now to prove a result like this, you need something more. You need bounds, word identities on the lattice, but also you need to exploit what is called emerging word identity. So you have to use the fact that the theory is close to a quantum field theory, which has other symmetries, in particular chirally symmetries, which are of course broken by the lattice, but then you have to exploit this fact. And then you have, so the idea is you introduce, in addition to the other ingredients, you have to introduce another model. You fine-tune the Bayer parameters of this other model so that the fixed points are the same, and then you use some symmetries of this model. So the model you need to introduce is a quantum field theory model like this. So this is really quantum field theory model because we have a linear dispersion relation. This model has word identities, but also chiral word identities. And then you have to use a property which can be proved rigorously. I don't know if in the course will be done, which is called non-perturbative, which is called non-renormalization of the anomalies. So the anomalies are broken of this kind of continuity equation, but then in the quantum field theory they are broken by extra terms. These extra terms are called an anomaly. These anomalies are not renormalized, they are not given by series of terms, and then using this universality of the chiral anomalies you can get this kind of results. So this is very roughly the strategy. So just for expert I show you a picture. So you have to consider word identities on a quantum field theory. Then, as you introduce a cutoff, you get correction, but this correction only contributes to this graph. All these other graphs vanish, so only this graph at the end remains. All these other terms you make a bounce by determinants, and then they go to 0. Okay, so this is very, of course, you cannot understand anything here, so just skip, and I go to the conclusion because I'm already late. So what we say, the conduction electrons are described by non-relativistic quantum mechanics, but in several materials, you can see maybe after this talk what I mean by this kind of sentences. They are a sort of lattice realization of quantum field theory models, so you can really is a very good arena to test renormalization ideas. For instance, I was very quick in the last part, but you see, it's exactly an application of the ideas of renormalization group. You have two models which differs by relevant terms, and you fine-tune the Bayer parameters so that the fixed point is the same, and then you use some symmetry of the other model. So why is used for the lattice? Because then you don't have any ultraviolet divergence, and you have these bounds. And by these bounds, you can get results without computing graphs. I mean, simply you can get some cancellation implementing word identities and bounds. So you see, there are no trivial divergences, so the constructive renormalization group here can be completed. I mean, of course, it would be much better to do the standard model, but I mean, we must content to end up this program and then to compare with experiments, so I think it's good. Of course, there are infinite many open problems. For instance, in particular, there are this class of objects which are called bytes and metals, which are similar to quantum electrodynamics in 3+1 dimension with a ultraviolet cutoff. So as the quantum electrodynamics in 3+1 on the lattice is very much studied, could be very interesting really to really say to compute some physical observable rigorously and compare with experiments. And also, of course, there are several problems like this. So maybe I stop here. And thank you very much.
So we are late, but eventually there is a very quick question.
Well, there was this remark about this real and imaginary frequencies and this analytic continuation. So did you really something? Is there some analyticity that you did that?
Yes. So in the this is quite a recent result we got for the first time, I think, for a couple of years ago for the Hall effect, I think. And then there is also there is in the paper with Giuliani and Porta about the Hall effect is proven. There is a lemma. Then we also proven with Porta in Journal of Statistical Physics. There is but the analytic continuation is possible only at zero temperature. We are very unable to move from zero temperature, so it's quite clear that we have to send first T2, but at least for that we are able to make the limit we can show that the limit from the imaginary times and from the real part is the same. It's a challenging problem so we got subplot in the complex plane, but of course we have also to use some bounds and also some a priori bounds obtained for lattice system by other method. But by that it's possible to make this rotation. Let me mention there is another very interesting physical question which is very much debated in the condensed matter. What happens to this analytic to this object when you are at finite temperature? In this case, it's believed that this continuation is problematic, and even there is some conjecture that solvable and not solvable models at finite temperature gives us different transport problems. So in that case, the relevant terms could really change very qualitatively the physical properties. So it's a challenge, I think, for constructive quantum field theory. If it is able, I mean, we are able to consider these irrelevant terms, but always at zero temperature. It's a challenge if you could really consider the role of these irrelevant terms when they are not irrelevant at all. I mean, they could even change completely the physical behavior at non-zero temperature. But that's, in fact, this is the reason why our proof, we have to send first beta to 0 and omega to 0, and we cannot really move at the moment that limit. But the limit is proven. But very recently, in fact, when this work on graphene, we didn't prove it, and only now we really completed the limit.
Yes, for the next question, it's better to wait a coffee break. We should go on with the next talk, so it will be the second lecture of. And so we say the speaker again.